Okay, so thanks to Joe for the invitation to speak at this new series that you yourself have organized for our department, which is great. Before I start my talk, I just want to ask a question to the audience. How many of you do dance recreationally, at least at some time during your... Oh, good, a lot. Wow, excellent. So you're going to be able to relate to this talk, I think. And those of you who don't, I think can still relate, but in a different way. So I'm going to turn the lights down to... No, not too much. Okay, too little. Too much. Okay, wait just a second. I've taught in this room before, so I used to know how the lights work. Okay, that's definitely too much, too little. Okay, we're gonna stick with this. You know, that's pretty much what I got before, but we're gonna stick with this for now. Anyways, so I teach a course here called The Arts in the Brain, in which I talk about not just music, not just dance, but this collectivity of the arts, their interrelationships. And my lab I call neuroarts because I work on music and dance, language, hopefully visual arts in the next year. But I just want to talk about the fact that I don't think about dance just as dance, but dance in the context of other art forms, other cognitive functions, and especially music and language. I won't talk so much about language today, but dance definitely shares with music the fact that it's done in time, it's done in rhythm, and also the fact that dancers have to synchronize with one another as well as synchronize with the musical beats. So we have this notion about entrainment or synchronization, which is common to music and dance. Dance is generally done to the beat of music. And then we don't think about dance so much as being representational, but in most cultures, especially most small-scale cultures, dance is about something, and the movements that people make are gestural. They convey something about meaning. Oftentimes people wear costumes, whatever, they're portraying the roles of characters. And so dance shares with language this notion about representation, especially through gesture. So what is dance? And so we can define dance for this talk. And this is actually a lecture that I give in my courses. So if you take my course, you're going to hear something very similar to this. Dance can be defined as a spatially patterned and rhythmically timed form of body movement in which a musical beat generally serves as a timekeeper. So implicit in this definition is the fact that there's a kind of spatial patterning. We're not just moving randomly, but particular patterns, directions, movement patterns. Usually it's done in rhythm to the beat of a musical timekeeper. Dance is a human universal, often associated with ceremonial rituals. It almost always involves music. As far as we know from anthropology, there's no culture that doesn't have some kind of movement that we would think of as being dance. It's thought to be universal, and especially associated with ceremonial rituals. And again, in almost all cases that we know of, dance is accompanied by music. Dance is done to the beat of music. Dance takes full advantage of the human capacity for representation, narrativity, gesturing, and mime. So again, we don't think about this in terms of our culture and salsa, but in many cultures, dance is a kind of gesture language. Like I said, people wear costumes, they portray characters, and their movements are iconic. They're representing some activity. And so dance is, again, a kind of gesture language. There are various ways to classify the dances of the world. I'll talk about just a few different parameters that have been used to classify dances. One is the number of dances, so you can dance solo, as we often do in discotheques in our culture. But in most cultures, people dance together in some form, and so we have things like pair dances or larger groupings we can call group dances. We can also classify dances in terms of the configuration of the dancers. So for example, a couple dance in our culture tends to be a face-to-face thing. But for example, when I lived in Sweden, we had couple dances that were done side by side. So there are different configurations. Even for a pair dance, you can dance in a line, you can dance in a circle. If the circle becomes connected some way through holding hands or using your shoulders, it can become a ring dance. You don't have to stand or have legs to dance. There are sitting dances. I'll show an example at the end of a sitting dance. So most dances do involve the legs and movement of the legs, but you don't have to be moving. And by the way, I just saw you. So there was a powwow outdoors today. So some of the things I'll be talking about actually were just happening right on the lawn before the talk today. So kind of a good coincidence of this powwow with my talk today. We can also classify dances in terms of what are the most active body parts, what are the functional joints. And so we can talk about different kinds of movements in dance, linear, curvilinear, rotation. I mean, some of the dances you might know, for example, say salsa versus tango. In salsa, you move your hips a lot. In tango, you don't tend to move your hips at all. And so there are different joints that are thought to be active and functional. In Indian classical dancing, like Kathak people, the eyes become a functional joint. And so you learn how to move your eyes in certain directions as part of the dance. Dances differ in terms of their energy. Some are fast, some are slow. Some have a constant kind of energy, and some have, big changes in tempo. They're a bit more jagged compared to smooth. Okay, so I want to think about the psychology, the neuroscience of dance. And so these concepts about spatial cognition come from psychology. This distinction between two different kinds of reference frames that are called allocentric versus egocentric. So we can describe things spatially, allocentrically, as one object compared to another object. So this cup in relation to the laptop case. So two things in kind of a Cartesian plane, Cartesian space. Or I can do it in terms of what is something in relation to me, egocentrically. So you're to my left, you're to my right. You two have kind of an allocentric relationship. We could talk about how many meters you are apart allocentrically, but egocentrically, you're to my left, you're to my right. I'm to your left, whatever. This is the reverse for that. Okay, so we can talk about things in terms of object to object or ego to object, so me compared to the world around me. We know from a lot of work in neuroscience, especially single unit recordings with monkeys, that there's not just a single unitary egocentric reference frames. There are multiple different reference frames in relation to different parts of the body. So there are neurons that are so-called body-centered neurons. We have eye-centered, retinotopic neurons, head-centered, hand-centered, and the like. And it's kind of this combination of different reference frames that makes up what we call our body schema. So it's not just one thing, just one place. It's a combination of different spatial reference frames, body, eye, hand, whatever. That combination make up our sense of our body schema. And again, we have different sensory modalities that contribute to spatial cognition. We can localize things based on sight, hearing something, the smell of, if you're looking for a restaurant, you can follow the smell of something. And so multiple different sensory modalities contribute to our sense of space. But I want to, in talking about dance, think about dance as being a so-called kinesthetic or proprioceptive art form, that the key sensory modality is not so much vision, as we might think about as being intuitive, but more our joint sense, which is called proprioception. So in our muscles, we have receptors called proprioceptors that tell us about the length of the joints and the degree of contraction. And so that body sense is called either kinesthesis or proprioception. And so again, for those of you who dance, you can probably close your eyes and do a lot of your dance steps without vision. Me as a tango dancer, I have to lead, so if I don't have my eyes open, I'm going to bump into people. But oftentimes, my partners, if they're very experienced, they can close their eyes and do all the steps that a tango dancer has to do because they're just kind of feeling the energy coming from my body, and she's doing stuff with her body based on her sense of proprioception. So vision's a very nice support sense if you don't want to, knock into people. But much about dance is this kind of joint sense, this proprioception, kinesthetic sense. And so I would say that dance is a kinesthetic art form. And so to kind of put these two concepts together, dance is a spatial art based on a kinesthetically guided spatial cognition in relation to this egocentric concept of our body schema. Okay, so several years ago, actually living in Texas, I conducted the first, and to this day, the only imaging study of dance movement. There have been several other studies about dancers observing dance, but they're not motor studies. They're just dancers watching dancers. This is the only study so far that has dancers actually moving their body in a brain scanner. And so I want to talk about three aspects, I think sort of the three critical aspects of the neuroscience of dance. One is this sense about navigation, how we move our bodies in space. Second, meter, the fact that we tend to move isochronously, 1, 2, 3, 4, this regular recurring beat that we call meter or isochrony music. And then beyond that, how we do this kind of metric movement, but how we synchronize to some other timekeeper, in this case, a musical beat. And as I'll play some examples later on, sometimes the beats of dance songs are very, very complex, and we extract these kind of strong beats from the music. So navigation, meter, and entrainment I'll talk about in sequence. Okay, so here were the subjects for my study. These were amateur tango dancers. I see some of the Hamilton tango dancers have shown up today. And so these are people like that, people who work day jobs and came in the evening to dance. These were not professional dancers by any means. They were amateur recreational dancers. 21 to 51, if you know if in psychology, this is a very, very old mean because most psychology studies like your 21 is the average age. Here, this is a 33-year-old mean. It's a very old group of people that I scanned for this study. They had on average 2.5 years of dance experience in Argentine tango and about 8 years of total dance experience. So this is Argentine dance tango that I'll be talking about. And for the most part, these were not musicians. They had minimal musical experience. Okay, so I'm going to talk about brain scans. Actually, I do need to, let's see, this one will be for this. Okay, we'll have a few of these where I have to turn the lights down. But in general, when you see a brain scan like this, like the kinds I'm showing today, you're actually seeing two separate scans that are superimposed. And so one of them is this kind of grayscale thing that you see in black and white, and that's the so-called anatomical scan. That gives you information about the structure of your brain. And for that, we use a technique called anatomical magnetic resonance imaging, anatomical MRI. Okay? So that's this kind of black and white thing you're seeing in the background. Then superimposed upon that, you have a separate scan where you have people actually do something. Look at the function of the brain. Which parts of the brain are active when you're actually doing something? During this, people tend to just go to sleep. They don't have to do anything to have their anatomy be shown. But for this, people have to be awake and alert, and they have to do something which you've told them to do. And there are two techniques that are used to get functional images. One is called functional MRI, another version of the MRI technique. The other one, the one that I used in Texas, is called PET, or positron emission tomography. And as you're seeing these artificial color, this is not, brain, this is not blood or anything. This is just an artificial color from a computer. But this color stuff is the functional scan being superimposed upon the anatomy, which is shown in black and white. And I want to point out that both of these techniques, fMRI and PET, these are indirect measurements of brain activity. They don't measure anything about the electrical activity, about action potentials, things you're learning about in your psych courses. These measure things related to blood flow. And so fMRI measures something about the oxygenation of blood in your brain, and PET measures something about what is the rate of blood flow. So if you do something, that part of your brain which is important for it will have a local increase in blood flow. So if I move my hand, the part of my brain that controls the hand has a local increase in blood flow. And so techniques like PET and fMRI can measure these changes in the blood parameters associated with performing some kind of activity. So again, this particular study is a PET study looking at local changes in brain blood flow associated with the activity. So another important point about brain imaging is that if I just have people do anything, just one thing, you're going to see the whole brain kind of light up. And so we have to use what are called subtractive approaches, get rid of all the background activity in order to see key brain areas for particular functions. So for example, here I'm showing a brain scan, two different activities. One, the person was speaking, and the other one, they were you say, okay, just lie there, don't do anything, just rest. And so we take all the brain activity from rest, subtract it away from that for speaking, and then you start to see specific activity associated with speech. If I just showed you speaking by itself, kind of the whole thing would be like a big red blob. Okay, so a lot of your brain is involved in just about anything you do. To see these kinds of specific activities, you have to get rid of some kind of baseline condition to get rid of all the other stuff. Let's say I did speaking minus speaking. So I did speaking, now I got rid of all the brain activity due to speaking. Well, as you expect, there should be nothing left. It's the same kind of thing. But how about in this condition? I have one situation where I say speak, another one where I say sing. Okay, speaking and singing are close, but they're different. So what you see is that here you have these two blobs when I have the rest as the baseline, but now when I have singing, singing kind of washes out some of the activity which is shared with speech, and so I see less in the speaking minus singing subtraction. As a general rule, the more the control task resembles your task of interest, the more it subtracts out brain activity that is shared, that is common to both tasks, hence the less you will see. I'm going to be showing pretty much minus rest tasks in this talk, but just to know that the more that your control task resembles your task of interest, the more it tends to wash out activity which is common. In this case, this peak was common to both. It tends to subtract it out. So I'm going to be showing subtractions all throughout this talk. Okay, so what did I have these people do? These, again, were amateur tango dancers. And so in the real Argentine tango, you keep on moving forward and forward and forward. So these people just be dancing their way out of the room. And so I had to do something else. And so I made kind of a little box step that was just, so it just went like, let's see, 1, 2, no, sorry, how'd it go? It went 1, 2, 3, 4, 5, 6. Okay, it's just a box step, but it was based on the basic step in tango is called salida básica. And so I just made kind of a variation of that happened to be a box where they didn't have to actually walk outside of the room. So 6 steps that were done like this. And so what's really important about this study is that the step was taught several weeks, a week or two before the PET scan. There was no learning going on. They knew the stuff cold. So this wasn't a learning study. This was just a motor study. They knew this task very well when they came in. Their eyes were closed throughout the whole thing, so there's no visual component to the activations. It was simply all their body sense, the kinesthesis. Okay, so no learning and no vision in this study. So I want to talk about the overall design, in general, what people did in the studies, because there were a number of conditions. And I'm going to show you videos for 2 of the conditions so you can kind of see what they were doing. One of them, the highest level, is called metric dance, and was simply this step, this basic step, done to the beat of tango music that was played in through headphones. That'll be kind of my most tango-like thing. I'll call that metric dance. They also had another condition which we're calling non-metric dance. And so we took tango music and we went to the wave file and we introduced artificially quickenings and slowings of the beat to make it sound very irregular. And now instead of being 1, 2, 3, 4, it's like 1, 2, 3, 4, whatever. Very unpredictable rhythm. So we call that the non-metric condition. And by comparing these two, the brain activities for these two, we can get a sense of what brain areas are important for this function of meter, of isochrony in dance. Another condition had people simply do isometric contractions. What does that mean? So this kind of a thing when you simply flex your muscle, but there's no movement of the joint. Okay, so here I'm just isometrically contracting the biceps, but now there's no movement if I just flex. So we have people just contract the same muscles they would use to move. So thigh muscles, gluteal muscles, but there was no movement of their legs. They simply went 1, 2, left, right, to the beat of tango, but there was no movement. And so by comparing these conditions with this, we get a sense of what brain areas are important for movement, for navigation, because this one had was matched for the force aspect, but had no navigation. So this kind of comparison allows us to see brain areas involved in patterning, navigation of movement. And then finally, we had this condition where people did the same pattern, but now there was no music. Okay, so they did the same pattern, but now there was no synchronization to a beat. And so this allowed us to determine brain areas that are important for this aspect of entrainment, synchronization of your movement to a musical beat. As control conditions, we had simply passive listening, where they didn't move anything of their body, they just listened to music. And then this kind of thing we call rest, just clear your head, just relax, don't do anything. Okay, and so here's a person who's not one of our subjects. She was a model that we hired, because we hire a photographer and a model to do this for a paper. And so she doesn't really have 4 legs. She only has 2 legs. But we wanted to give a sense of what our subjects were doing, so we had this kind of fancy photography here. And so our subjects' feet were placed on this inclined surface that we could measure their movements. And so this is the PET camera right there. The next one actually shows one of our real subjects. And so his head is cut off here because we have to protect his identity and all this. We can't show you who he is. And so here's the PET camera right there. This is his body. Those are his legs and his feet. And you see that his feet are on this inclined surface, inclined about 45 degrees. Okay? We have this digital camera looking down at his feet. And if you look down, what you'll see are his feet, like this, on this grid that we can kind of measure his movement. So I'm going to show you 2 of the conditions now as videos. So the first one is the metric dance condition. So this movement done, in a regular beat to tango music. It looks something like this. Okay, so he's performing that step that I showed you a few slides back, that basic box step, to the beat of metric tango music. Then we have this non-metric condition, again, where we artificially altered such that the average time was still the same. So the average rhythm was exactly the same, but there were local changes in the rhythm, and it looks and sounds something like this. Okay, so again, on average, it's the same average rate of movement, but now this is very unpredictable, and so the subjects told us afterwards this was very hard to follow. It was difficult for them to synchronize to this because it was not this regular metric beat. Okay, so which one do I have? This one. Okay, so let me I don't know what your neuro background is. It's not one of my classes, so I just want to give an overview of some of the brain areas I'm going to talk about in my slides. So the first one I'll talk about, or one of the areas, is the so-called primary motor cortex in the prefrontal gyrus, which is very important for the voluntary control of body movements. And so I'll talk about this motor cortex here. So here we have the frontal lobe, and here is the parietal lobe. I'll talk also about this superior means upper, superior parietal lobule here, more in the back of the brain. And I'll talk about two structures that are sort of deep inside the brain. So one of them is called a collection of nuclei called the basal ganglia, shown here. And then this large structure in the back of the brain called the cerebellum. Those are kind of the main areas I'll talk about in my slides. So let's talk about the results and these different contrasts that I've looked at. So the first one is to look at this spatial patterning of movement, how we navigate in space. And again, our way of looking at that is to take the brain activation for this metric dance that I showed in the first video and subtract out all the brain activity for simply contracting these muscles but not moving them. So just getting rid of all the force and leave all the spatial stuff behind. So this one has contractions plus leg movement. This one only has the contractions, but there's no movement, so there's no navigation, no patterning. So whatever's left over should be sort of a reflection of brain areas important for spatial patterning of movement. So the first thing I want to point out is that simply doing this kind of isometric contraction where you don't move your body is a very effective stimulus for this motor cortex. I always thought the motor cortex was involved only in movement, sort of until I did this study, and I saw that just doing this kind of, this contraction of the muscles but no movement is actually a very good stimulus. So this is contractions minus rest, and we see a very strong activation of this primary motor cortex of the prefrontal gyrus. But now what happens when we start to do this more dance-like activity, the metric minus rest? Okay, one more thing. So just to point out that this motor cortex is organized in this kind of topographic, or we call somatotopic manner. And so you see kind of a map. So here we have the brain. We've taken a slice like a loaf of bread, opened it up, and we see this. We see kind of a map of the body, of the body's muscles. And so kind of three domains. We have the facial region here being the lowest. Then we have this large area for the fine control of the hands, the digits, and all that. And then you have the lower extremity, the legs, occurring towards the midline here. And that's kind of what I'm showing in the previous slide, is the midline of the brain. And we're seeing kind of this leg, the leg area of this map here being activated when people have to move their legs. Okay, so this is what's shown, what happens when you have just contraction of the muscles but no movement. But now if people do this kind of dance-like activity that includes contraction but also movement, we see a much more extensive activation in the midline. And now if we subtract out contractions from meter, what's left over that should reflect this kind of patterning, the residual activity is mainly found here in this superior parietal lobule. So again, we have this for just contractions, this for the dance kind of movement, subtracted out, and what's left over, what's residual, is the parietal lobe for patterning. And the parietal lobe, if you've taken psychology, you know it's kind of the really essential area for spatial cognition. People who have lesions damage to their parietal lobe have a lot of problems recognizing things in one hemifield or navigating, putting their hand in a slot in the appropriate orientation and all that. And so they're thought to be sort of in the human brain two basic domains. You have this inferior parietal lobule here and the superior there. And they have some similarities and some differences. The inferior parietal lobule is thought to be most important for visual guidance of movement. And so it gets its major input from extrastriate visual areas in the occipital lobe and projects to motor planning areas in the frontal lobe. So it's kind of this in-between spot between vision and motor activity. And so this area is thought to be very important for visual guidance of motor activity, so grasping a bottle, whatever you do that's visual guided. The superior parietal lobule also has a visual component, but in addition, it has this kind of somatosensory proprioceptive component. So it's not just vision, but also the sense of touch and proprioception is found in the neurons there. And so that seems to be a good area in terms of dance navigation, that you have not just the vision, but also this somatosensory input coming here from the postcentral gyrus. And so I won't make this too detailed or too clinical, but for us, this area kind of represents a body map of egocentric space based on not just visual cues, but these proprioceptive kinesthetic cues. And this gets a lot of support from work on the monkey, which I won't go into here. But this superior parietal lobule is thought to be very important for not just visual guidance, but kinesthetic guidance of motor activity. And so for us, it seems to be a good area for being an area of navigational area for dance movement because of this kinesthetic component. So I won't go into much more detail for this lecture, but And one thing I just wanted to point out too is that I think most of you heard about Broca's area, this very important speech area, which when lesioned gives rise to speech production areas, deficits. And so we found that in all the motor conditions, so motor contractions, whatever, but not listening alone, we see activation not in Broca's area, which is in your left hemisphere, but in the right hemisphere homologue of Broca's area. So it's called right Broca's area, or the right homologue. And so all of these conditions that had movement showed activation in the right homologue of Broca's area. And so it was thought for a long time the Broca's area was simply just a speech area. Now it's thought not to be speech specific, but much more about sequencing. And so dance is also a very sequenced motor behavior. It's not the same thing as speech, but it involves this kind of complex string of sequences. And so this kind of fits, so the fact that dance activates the right homologue of Broca's area fits in with the current concept of Broca's area is less of a speech area and more a complex organizer of motor sequences. Okay, so that's kind of the story for this spatial navigation aspect of dance. So Broca's area, right homologue, superior parietal. Let's talk about the rhythmic or the timing aspect of dance. And so here it's important, and I talk about this in my classes quite a bit for my students, to distinguish on the one hand meter versus entrainment. So meter is any kind of regular, equal timed pattern of movement. So 1, 2, 3, 4, just equal durations between beats or pulses. This is the same thing, but corresponds with your ability to synchronize your movements to that kind of timekeeper. So I give the example of walking versus marching. If you're walking, going 1, 2, 1, 2, but it's just very self-paced. But now if you have to march, you have to synchronize that same left-right to some kind of external timekeeper. You have to entrain. This is more like just a self-paced kind of thing. This you have to actually synchronize those movements to a timekeeper. And what we know from the study of animals is that meter is kind of the norm when it comes to animal locomotion. So if you're a fish, if you're a bird, you tend to have alternation of the left and right sides of your bodies. But this kind of entrainment phenomenon is extremely rare and found in humans and a few other animal species. So for this, we know you only need nothing more than a spinal cord is sufficient to have, we have these so-called central pattern generators in the spinal cord that generate this kind of left-right alternation. But this seems to require sort of higher centers of the brain for entrainment. So for us, we wanted to examine meter and entrainment. So for meter, I showed you the two videos of metric music or metric dance, non-metric. We want to do this comparison between this condition that has regular, predictable pulses and this condition that has these irregular, unpredictable, but on average the same tempo, the same rate pulses, and see what's different between the two. And so the main difference we found in this contrast is that the metric condition activated a part of the brain called the basal ganglia, a component called the putamen, and the non-metric didn't activate it. We saw much less activity in the basal ganglia, the putamen, for non-metric compared to metric movement. And this is actually a very complex circuit. So the basal ganglia, if you've taken psychology, you've learned about this subcortical circuit, a very, very complex circuit. My students have to kind of suffer through learning about all the different pathways of the basal ganglia. But kind of the bottom line of the basal ganglia circuit is that it's most active for regular, predictable movements. And so the example I always give is if patients who have Parkinson's disease have a lesion of this pathway, and so they're very good, they're very bad, so let's say, at initiating movement or making changes, but once they get, so you say, okay, I want you to walk, they have a lot of trouble starting, but then they finally get going, whatever, you say, okay, now I want you to turn around. And so they have problems making these changes. When things are very predictable and regular, that's where they're okay. When they have to initiate or make changes, that's where they have problems. So this circuit is thought to be really most active when motor control is regular, predictable, and less active when things are unpredictable. So in our case, seeing this putamen activity in the metric condition and not in the non-metric condition fits in very well with the literature, especially the animal literature, on how the basal ganglia operates. So that's something about this voluntary control of meter. And I also want to point out that, the example of tango was probably maybe one of the simpler kinds of rhythms, but in world dance, actually, some of you may know, but on Friday nights at one of these churches in Westdale, I don't know what they're called, but they have international folk dancing, and you have much more complex rhythms. So here's, I think Macedonian, I forget what. So a more complex rhythm to entrain to. So, I mean, human musics have a lot of diversity of the rhythms that are found. And actually, when I lived in Sweden, the major folk dance is this polska. And the polska, which is not the polka, it's called the polska, is actually in 3/4. So, you know, a 3/4 like a waltz, 1, 2, 3, 1, 2, 3. See if you can find the 3/4-ness of a polska. Anyways, again, you know, this is a dance. I used to do this in Sweden. I can't do it now because it's too difficult. But you dance side by side with your partner. Then you go in front. You have to turn like this as a pair. And it's really difficult. But to find the beat was kind of the first big challenge of that music. Find the beat, then I can start doing these turns. Okay, so this issue about entrainment. How do we entrain to an external beat? And so, again, here we compare this condition where people had to, the metric condition where they had to entrain to the beat of tango music. And then, again, doing the same thing, self-paced. There's no entrainment signal. It's just at your own pace. The tempos were made to be the same, things at the same tempo. What's left over? So again, motorically, it's almost this, like walking and marching, almost identical. Just one happens to have a pulse saying, do it at this tempo. And so, again, most of the brain areas were similar, were subtracted out. What was left over was activity in this other subcortical area called the cerebellum, especially in this midline region called the vermis. So this is metric minus motor, gets rid of almost all the brain activity, leaves principally activity in the midline of the cerebellum. And so there's been a lot of debate about whether the cerebellum could sort of be the metronome, the timekeeper of the brain. And so here's kind of the structure in cartoon form of the cerebellum. So the cerebellum receives input from most of the sensory systems, so the vestibular system, auditory, visual, somatosensory, and then has these somatotopic maps. You see body maps all throughout the cerebellum. And so it's kind of a good candidate for being a metronome. What would we want in terms of what would be the candidate features of a metronome in the brain? At least 3 features would be expected of a neural metronome. One is that its activity, its neural activity, varies with tempo. And that's been shown very clearly that the cerebellar activity, its activity will increase with faster tempo, say, in a finger tapping study. What's important for human entrainment is that we can do it to not just musical beats, we can do it to flashes of light or taps on your skin. So it's not just about sound. We can entrain to all different sensory modalities, so vision, touch, sound. And so does the cerebellum have all these different sensory modalities? And it definitely does get input from all these different sensory systems. And finally, if you look at the way people can entrain any part of their body to a beat, you see people tapping. Some people are doing this, and some people are doing this. I mean, every different part of the body kind of gets recruited for entrainment. And so again, the cerebellum has all these different somatotopic maps. We have full body maps in the cerebellum. So at least for right now, it's kind of our best guess of what is the metronome of the brain is the cerebellum. Again, it's still controversial, but it's kind of my working hypothesis for right now at this point in the field. So I want to talk about another, so this subtraction between metric and motor yielded one other sort of unexpected result. And it relates to the fact that people unconsciously move their bodies. So if you're sitting in a club and you hear music, you're going to start doing something, you're going to start moving, unconsciously in many occasions. And so we kind of had some insight into this unconscious entrainment. And so in this subtraction, we saw this activity in a part of the brain called the thalamus, a nucleus called the medial geniculate nucleus. In the auditory pathway going from the ear to the brain, this is one of the relays in that circuitry going from your cochlea to your auditory cortex. This is kind of the next to last relay before going to, here's the auditory cortex shown on the side, but this is your subcortical auditory nucleus. And so we thought, okay, the reason why we're seeing this activity in this subcortical relay is because this one has music, this one doesn't, and so that just reflects the fact that there's the presence of music in one condition or the other. But we could control for that because we also had a listening condition. So we have people simply listen to music. And if we subtract out all the brain activity for listening from that, it stays there. So it's not really a function of the fact that there's music there, but it really is a function of entrainment. This is a part of the auditory system which is active, not just in the presence of sound, but in a situation in which there's entrainment going on. And so we've proposed our low road hypothesis, and that's the idea that you don't have to go to the Royal Conservatory to learn how to tap your foot to the beat. It's something very, very fundamental, very low level. You don't have to learn about harmony and keys and all that kind of stuff to know where the beat is in music. It's kind of low level information. And so we're proposing that beat information is processed, say, more subcortically, more outside of the realm of awareness than in a more cortical fashion. And so we're calling this kind of a low road hypothesis. All you need is kind of your subcortical area, your thalamus, going to your cerebellum. That should be sufficient for having all this unconscious entrainment to be such that when you just tap your finger to music, you're not even aware of what's going on. So that's kind of a summary of our imaging study that was published in Cerebral Cortex in 2006. I want to conclude with some speculations I have about the origins of dance. And it's very fitting that we had the powwow dancers because it's exactly what I'm going to talk about. And so the first one I call this a body percussion hypothesis. And that's that dance evolved first and foremost as a sounding phenomenon. And so if you look at these powwow dancers who were here, they had their regalia, and especially the women, they had all these metallic pieces attached to their costume that every step they took, every movement they made, you heard clank, 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 clank. So they essentially became percussion instruments. So every step they took as dancers, they became musicians in the percussion sense. So according to this hypothesis, there's no real distinction between a dancer and a musician, at least as a percussionist. And so the dance and rhythmic music co-evolved. And so I'm going to show you in a second a video of this kind of body percussion. So it's not just regalia, but all this kind of stuff like, which you see in many world dances, people, this kind of stuff. There's a lot of body percussion. But what's very common is that people attach things, for example, leggings, or things to their costume that as dancers, they make a lot of noise. And so I propose that dance evolved from its origins as something not silent, but something which is sounding, and that you become sort of a percussionist in the process. And you find this throughout the entire world, this kind of body percussion. So it's not specific to one region or another. And then secondly, people think that dance is just simply showing off energy, all this kind of stuff, being the big man, whatever. But dance is very much a gesture language. And if you look at dance in small-scale cultures, it's not just dance for its own sake. Okay, I want to show off. It's a narrative function. It's something about telling stories. Again, people put on costumes. They tell about the history of their culture. So they portray their ancestors, their gods, whatever. And through their movements, they portray those characters. And so all these movements, again, in small-scale cultures, they tend to be iconic. And so dance is narrative, is kind of a gesture language. So I didn't know how much time I was going to have. I just brought one example today, but it's from Samoa, and it shows dance. You're going to see a combination of this kind of body percussion. And again, I don't know exactly what the narrative is here, but everything they're doing with their hands, they're telling a story. So everything is iconic in their movements. So this is several dances taken from Samoa. I need to just set up the video for a second. So again, it's kind of gesture language with the hand movements here. It's a sitting dance too. So you see these leggings that the guys are wearing. Okay, so let me just... Sorry, back to me. So I talked about, that we have more than one kind of representational system. So here we heard words. They were singing words. So we saw this combination of language, but also body gesture. These two things that are working in parallel to convey meanings. We heard music, we saw body percussion, and the whole thing. So again, just some speculations about the origins of dance. It's not just about, okay, look at me. That could be part of it too. That is part of it, but there's a lot more than that. So I would propose that there are sort of two parallel channels that we have in communication. We have this song/speech route that involves the voice, and then we have this percussion/dance route that involves the rest of the body aside from the voice. This one focuses more on the pitch, melodic aspect of music and speech. This one focuses more on duration, intensity, rhythm. This one gets associated with one particular representational system that we call language. This one more with another representational system that we think of as gesture. And these two things get combined all the time when we have dance and music. We just saw words and music, body gesture, body percussion, and the like. So that's my talk. And before I finish, that's my scientific talk. I also want to do a bit of community service because I'm part of a particular dance community here. So Zubair, if you would mind just presenting yourself. This is Zubair Sayed. He's a tango teacher in town, and I'm part of this group here. If you'd like to learn how to dance Argentine tango, Zubair has a website called gtatango.com. He's a great teacher, a great guy, always looking for students. We dance, it's Monday nights in Hamilton and Wednesday in Dundas. Okay, so if you live either in Hamilton or Dundas, want to learn beginning level Argentine tango, Zubair is the man for you, and so seek him out after the talk if you'd like to learn about lessons. That's my community service for today. Now I'll take questions. I'll leave this up.